All right, so here we are, and we are looking at the lab that we're going to be running for Module 1. Um, oh my goodness, I lost my pen again. You know, we're early enough that I can restart, but I'm not going to. I'm going to try to find this thing. And I'm just going to ask you guys to bear with me while I do. There's like not a huge amount of stuff on my desk. I bet is it in my pocket? It's not in my pocket. You know what? I'm just going to get another pen. And hope that I don't run out of pens over time. All right. So, let me double check that this is still... Nope, that's definitely way off center, because I moved it. That's what I get for moving it. Okay, so question 1. We want to know what the period for a signal with a 20 hertz pulse is. Alright, so a signal with a 20 hertz pulse, and we want to know what the period is. Alright, so we need to grab one of these formulas that we have listed up here at the top. Now, the first one, frequency equals 1 divided by the time in seconds. We don't know the frequency, so we're not going to go with that one. Now, for the second one, we have the time in seconds, which is, we can do either the time or the period between pulses. As the time, or as 1 divided by the frequency. So this here will give us period equals 1 divided by frequency. We have the frequency. So what this will look like, and let me turn this back on over here. All right, so we've got our period, t, and that is way too high. Let's come down. We've got our period t, and that is going to equal 1 divided by our frequency of, I believe it was 20 hertz. Yeah, 20 hertz. And like with anything in math or science, make sure you've always got your units represented there. That's very important. So we're going to do 1 divided by 20, and go ahead and use a calculator for that if you need to. I usually use one, especially for dividing small numbers. So we get that t is equal to 0.05 seconds. And this will actually be our seconds per cycle, will be our period. So 0.05 seconds per cycle. If we wanted to represent that a slightly different way, we could go back to our charts and say, convert this into milliseconds. So we do that, moving the decimal place over 3 points, and we end up with 50 milliseconds, which we can represent as ms per cycle. And one way of saying per in mathematical notation is by doing that little slash there. So 50 milliseconds per cycle. Both of these are correct. This is just perhaps a slightly easier way to say the same thing. Now, going to question number 2. If a computer runs at 3.2 gigahertz, what is the period of its clock signal? Now, once again, we are performing the same thing. We want to know what the period is. And that will be 1 divided by the frequency. However, we mentioned before, but that is the frequency in hertz. So in order to do this accurately, we need to get that 3.2 gigahertz into hertz. Now, giga, we will know, is 10 to the 9. So in order to turn this into gigahertz, we will go 9 spaces. All right, which gives us a pretty big number. That pretty big number is actually 3.2 billion. So we'll do 1 divided by 3.2 billion. And that will give us, I'll drag my calculator over here, but that will give us a really, really tiny number. So that will be t equals 0.0, and I'm going to count the number of zeros here so that I could be a little bit accurate. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Got ourselves 9 zeros there. 3, 1, 2, 5. All right, so there's a couple of ways to represent this, but we are going to, because we know we have to get rid of 9 zeros, so we could just get rid of those 9 zeros, 10 to the 9, and get 0.3125 nanoseconds per cycle. But we're going to take it one step further, and we're going to go down to pico. All right, which means 10 to the 12. So we bring this over 12 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we will get rid of those leading zeros, and we will say t, or the period, equals 312.5 picoseconds. So we could do picoseconds, or we could do PS per cycle. And one of these days I'll learn how to spell cycle, and then we'll all be having fun. All right, now we want to calculate frequency. So our frequency is going to be, oh, hold on. Let me actually let you look at the question. So right here, we have, if the period of a periodic pulse train is 500 nanoseconds, so we know the period this time. What we want to know is, what is the signal's frequency? So we're going to use this first formula here, because we don't know the frequency, but we do know the period, or the time in seconds. All right, so our frequency is going to be equal to 1 divided by the time in seconds. Now, real quick, you notice when we looked at the question, that was the time in nanoseconds. So how do we work from nanoseconds back up to seconds? Well, we will do 10 to the minus 9. So we will move our decimal place. So let's put the 500 somewhere over here so we can see for a second. So that decimal place is right there. We just don't have anything after it, so we don't represent it. And we will move this to the left 9 spaces. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And then we can drop these extra zeros. We don't need those for what we're doing, but that is 0.0 0.0000005. Okay? So we can bust out the calculator for that one because that's going to 0.0000005, if that was enough zeros. It goes into 1 quite a few times. As a matter of fact, it goes into it 2 million times. All right, so our frequency is going to equal 2 million hertz. Now, with hertz, just like with anything else, we can simplify that a little bit. So instead of saying 2 million hertz, so how many zeros do we have here? We have 6. 10 to the 6 is mega. So our frequency can be simplified as 2 megahertz. MHz. All right. Now we are down to our last question. And I'm dangerously close to having to flip the page over. We'll see if we can avoid it, but I'm not sure if we will be able to. Actually, I might flip the book around. And don't get confused if you see some upside down stuff. This might not be the right answer. I don't know. It'll be fine. But we have the period of our pulse train is 120 microseconds. Now we want to achieve a duty cycle of 20%. So let's go up and look at our formula for a second. So our formula is going to be that, oh yeah, no, that is way off. Might have been easier just to flip the page. Let's flip the page. Beautiful. Okay. So our formula is going to be that duty cycle is equal to the pulse divided by the period times 100%. Okay? So we know the duty cycle. The duty cycle is 20%. So 20% is equal to our pulse width, because we don't know what that is yet, divided by our period, which will be that 120 microseconds and actually let me okay, so micro is 10 to the minus 6. So we've got that 120 microseconds times that 100%. Now we are dealing with a percentage, so we actually wouldn't really need to convert units, so that should be fine. Now if we want to get rid of this 100%, we can go ahead and kill these percentages and just come over here and move that decimal place over. So that becomes 0.2 is equal to the width divided by 120 microseconds. So, in order to get this bad boy over here by himself, we basically have to reverse the operation that's on this side over to this side. So we are dividing this by 120 microseconds, and we will come over here and convert this into, and oh, hold on. See, I did ms here. Ms is milliseconds. And I just noticed we've got two ways. So when you're typing this out on a keyboard, I would advise to represent microseconds as that little, just a U. You could just do a regular U, or you could do the U with the little stick. Now, in actuality, microseconds are described with a character from the Greek alphabet known as mu, which actually looks a little bit like a backwards U, which I can actually show it to you a little bit. But there's that little dude. It's really, there's a fine line in representing mu properly. For those of you that have taken probability and statistics, I know mu is a common operator in some of those equations. But we will focus on using the U to represent the microseconds. I almost forgot about that, and that would have been tragic. All right. But what we're doing is going to be the same thing. So we're going to take that 120, multiply it with 0.2, and that is going to give us 24. So 24 will equal there. Bam. Now, very specifically, this is 24 microseconds. Remember, we didn't convert the units, which is fine, as long as we make sure that we keep the units the same. Because if this were 24 milliseconds, it would be a very different answer than microseconds. So make sure to keep the units the same, but it's fine that we don't convert them back to seconds. So the answer here would be 24 microseconds. All right. And that is the end of what I'm going to cover here. So the rest of the questions, we've got a true and false question. We've got a couple of short answer questions. I'm not going to work through those with you guys. Just, refer to the book if you need specifics on a definition. Go back to the lecture. You've got options. So we'll go ahead and do the rest of that way. But I hope you got something out of this.